Let's talk chemistry with Pastor Dan. We're going to continue looking at the periodic chart. We're going to do a quick review here because the concept, right there, highlight that, the concept we looked at the periodic chart, we identified that before. Now you can look back at the last video of all these definitions. Periodic chart is organized representation of elements by increasing atomic number. First came up with a scientist named Dr. Dr. Dmitry Mendeleev. Mendeleev was a Russian. He organized it by atomic mass and light character. Now, the light character was a good thing. Atomic mass, not so much, because there were basic holes. And he said, elements not yet discovered, which was true, but it also wasn't quite right. So Dr. Henry Moseley, British, came around using a cathode ray tube in calculus, reorganized it by atomic number. And it's a chart we basically use today, although we add new ones as we discover them. Now, we discussed in the last video classes, metals, nonmetals, semi-metals. Remember, metals have a luster, they're malleable, they're ductile, conductive. Nonmetals are brittle, dull, and insulative. And semi-metals, or metalloids, have characteristics of both metals and nonmetals, like aluminum, which is ductile, malleable, has a luster, but is not conductive. We also discussed valence electron numbers, and we counted the number of columns to do that. And we discussed ionization energy, electron affinity. Were actually numbers, but we found a way to identify them using first and second, third, 0, D and K for ionization energy, yes and no for electronegativity. We also talked, electron affinity. Electronegativity is scale values 1 to 4, and we just compare those diatomics we discovered from there. Now again, if you need to go back to the last video, review over those concepts. Last thing we'll look at periodic chart is families. Now families are also referred to as groups, and they're defined as characteristics. Now those are the columns, so those valence electron numbers, there we go. Same thing, characteristics are in those columns. Now the other way we can organize in the chart, and we'll look at this later, is by energy level. Those are the rows on the periodic chart, and they give us a concept of size. We'll talk about that in a few days. So let's start looking at these. The first one we'll look at here are the alkalis. Now the alkali is the first column, the very first column, and they have one valence electron because of the first column. Now I include hydrogen here. It really doesn't quite fit because the rest of these are all metals, but there are some similar characteristics that we have, so I throw it in here anyway. They are explosive, and I'll show you a video that shows that in a second, and they're extremely reactive. Sodium's so reactive that if you held it in your hands, well, first of all, it doesn't look like it has a luster because the instant it's exposed to air, it immediately oxidizes and begins to get a really dull finish. If you hold it in your hands, you'll feel like your hand is soapy. The reason is the sodium will instantly react with the fat in your hand and convert that into soap. So it is extremely reactive. Let's show the video here that involves, this is the last member of the alkalis that they're going to have there, which is, I believe, cesium. So here we go. Let's hit play. See what happens. Yeah, I don't have cesium. That's a little reactive there. All right, let's go to the next group. Next group is called the alkalines. Now, it's right next to the alkalis on the chart: beryllium, magnesium, calcium, strontium, barium, and radium. It has 2 valence electrons. That's the characteristics. They are exothermic. When they react, they give off heat and energy, and they are reactive. Not nearly as reactive as the alkali, but they are reactive. Let's show another video here that shows that. Okay, this is dry ice, carbon dioxide, and we've got a magnesium group here, and we're going to
Magnesium is placed
light
in
it
a
up.
cavity in a block of dry ice. The magnesium is ignited. And covered with another block of dry ice.
Now we showed that reaction before with magnesium. Very bright light. Now there's no air in there, it's only carbon dioxide.
Despite the absence of air, the magnesium continues to glow due to its reaction with carbon dioxide.
Extremely energetic.
Because of this reaction, Carbon dioxide cannot be used to extinguish magnesium fires.
Here we go. Let's stop that one right there. So that's alkalines. Now we're going to do that next D set. The D orbitals are. They do have 2 valence electrons, but they have a lot of stuff going on underneath. Remember, they're filling in the D underneath there. They're all metallic. They're all metals. And they vary from there because there's a huge range. So we really can't get many characteristics that are consistent through that from there. All right, now the next ones are strange because they really aren't that common. But what we do is we identify them with the number of valence electrons, and that's it. So boron group has 3 valence electrons, and that's it. That's the only common characteristics. Carbon group, it's from carbon down, has 4 valence electrons. Nitrogen group, you got it, has 5 valence electrons. And oxygen group, it has 6 valence electrons. And that's the only common characteristics of them because you have everything from boron to aluminum. There are quite a bit. One's a powder. The other is a metallic looking substance. It's a metalloid actually. They vary. I mean, go down to gallium, put in your hand, it melts. There's a lot of varying characteristics there. Now we come to the ones that are similar again. Next one's the halogens. Now this one's really interesting. Remember, most of these are diatomic. They're so electronegative, they can't exist by themselves. They have 7 valence electrons, and that's important because remember, we're most stable when we get to the filled shell. So we only need 1, and it wants that one something fierce. So they are extremely reactive. Fluorine is so reactive that if you try to ever breathe that in, you're dead. It'll kill you instantly. Chlorine, we used back in World War I as mustard gas. Bromine's a liquid. It's one of the only 2 elements that are liquids on the chart. When I worked in industry a couple summers, I was in college, a lab tech spilled a small bottle of bromine. The gas was so toxic that came off of that you'll notice occasionally I cough. That's caused by bromine. Iodine, it is the other characteristics of their poison is, wait a minute, they use iodines in cuts, and that's right, iodine in alcohol. But what that is, it's poisonous not to us, but to bacteria. So I've got a video here with iodine, so chlorine. So let's take a look at that. All right, so the formation of calcium chloride.
Sodium metal
So you can
is
see its
heated until it
reaction.
melts and just begins
So that's
to
chlorine
burn.
gas right there. And we're going to heat some heated sodium
Then
metal.
it is immersed into the
Put 'em
yellow-green
inside of it.
chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame.
We're forming salt here.
It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride.
Okay, that's enough right there. That's the salt that's
Afterwards-
formed. All right, so they're poisonous, extremely reactive, 7 valence electrons. All right, now noble gases, they're the last column. They have 8 valence electrons with the exception of helium. Remember, helium only has 2 because that's a filled shell. They're unreactive or relatively. I mean, we can make fluorine react with occasionally chlorine, but they don't want to react with much. That's why we call them inert gases, and they're all gases. All right, last look at the rare earth metals. Those are the Fs on the bottom. They can have 2, a lot of stuff going on underneath there, adding the F shells. They're rare. In fact, many of them are man-made synthetics. They don't exist naturally, and they're radioactive. They give off energy. They're so large, the second they form, they begin to break down and go their own way. So we had this before. Let's go through and identify. Why don't you go through the chart, see if you can come up with what the families are for each of those we did before. And there's our answers. And then let's finish that chart up. Okay, so take and do this all the way through, and then we'll go over it, pause it, and then we'll go through this. Ready? Pause it. All right, answers. There we go. Hopefully that wasn't too bad. Take care. God bless. Have a good day.